Okay, well, welcome back to College Physics 1. We're getting through our section on mechanics. So we have talked about some basic information, units, trigonometry, and vectors of how we're going to approach our methodology for doing mechanics. We talked about motion in one dimension. We talked about motion in two dimensions. And our last lecture, we talked about Newton's law of motion. So now we're going to get into energy, which could be another very interesting thing, and it'll also complement this whole section and that we're finishing up with this lecture. So on to topic number 5, chapter number 5. So in this topic, our goal is to develop a better understanding of energy and how to quantify it. Energy is present in the universe in many different forms, including mechanical, chemical, electromagnetic, and nuclear energy. Even the inert mass of everyday matter contains a very large amount of energy. Although energy can be transformed from one kind to another, all observations and experiments to data such as the total amount of energy in the universe never changes. It maintains as a constant. That's also true for an isolated system, which is a collection of objects that can exchange energy with each other, but not with the rest of the universe. If one form of energy is isolated, in an isolated system decreases, then another form of energy in the system must increase. Understanding how energy changes from one form to another is essential in all of sciences. So in this topic, the focus is mainly on mechanical energy, which is a sum of kinetic energy, and energy associated with motion, and potential energy, the energy associated with relative position. So once again, where we're focusing on this kind of material related to mechanics, and we'll get into other types of energy as we get into later sections in the class. So let's do a few reading question summaries, and we'll get into the main lecture material and go from there. So for this first one, for the beginning of the chapter, the gravitational force exerted by the Earth on the moon holds the moon in an orbit around the Earth. Let us assume that the orbit is perfectly circular. The work done by the gravitational force during a 1 week interval in which the moon moves through a displacement in its orbital path is what? The answer is 0. So we're talking about an orbital path, so it actually goes back to its place where it was before. And so the lunar cycle on in general is roughly on the order about a month. And so that's the approximation we're thinking about here. So the gravitational potential energy of a system it depends on the reference configuration for 0 potential energy. And so you have to be making sure you have your reference configuration laid out before you can figure that out in detail. What about which of the following is or are conserved in an isolated system? And so the answer is the sum of kinetic energy and the potential energy. So we're talking about mechanics, and these are the energies that we're referring to. And so with a closed system, there is a conservation of energy, and we're focusing on kinetic and potential energy here. And we'll get a little bit better understanding of the potential energy. Say you move a book up on a shelf, it has more potential energy than if it's on the floor, and et cetera. We'll talk a little bit more about how those come about. So consider 2 slides, both are the same height. One is long and the other is short. From which slide will a child have a greater final speed when sliding off? And you want to assume that there's no friction is acting. And so the final speed will be the same for the child as on the longer slide as it is for the child on the shorter slide. So you still have the same gravity, the same friction. And so that's what we're trying to give some perspective with this question. Maybe an example of something you can do with a simple experiment if you wanted to see how that might work out. And with some of the lab work associated with class, you'll also get a chance to see some of that. So here, a ball is thrown straight up in the air. At what position is the kinetic energy a maximum? And at what position is the gravitational energy of the ball or system a maximum? Consider only the trip up. So the answer for here, the maximum kinetic energy occurs at the point of release, and the maximum gravitational potential energy occurs at the top of the ball's trajectory. So a couple things for you to be thinking about as we're getting through this material. And our last reading question, in the case of force varying with position, what feature of the graph of force versus position represents the work done during a displacement? And the answer is the area under the curve. And so hopefully when we do some of our graphical analysis, you'll get a better understanding of how that would work. Okay, well, let's move on to the material in the discussion part of our lectures. And so as we're talking about energy. So here we have a constant force in the same direction as the displacement delta x. And so therefore the work that is done is F times delta x. So work has a different meaning in physics than it does in everyday usage. So you might want to be mindful of that. And so in physics, work is done only if an object is moved through some displacement while a force is applied to it. Doing work involves applying a force to an object while moving it a given distance. You might be tempted to think of work as F times D, where F is the magnitude of the force acting on the object and D is the magnitude of the object's displacement. But this only gives you the magnitude of work done on the object when the force is a constant and parallel to the displacement, which must be along a line. This works for certain cases, but in general, a more sophisticated definition is required. So the figure shows a block undergoing a displacement delta x along a straight line while acting on it by a constant force F in the same direction. The work done on an object by a constant force during a linear displacement along the x-axis is given by the equation here, where F of x is the x component of the force and delta x is x sub f minus x sub I is the object's displacement. Notice that in one dimension, delta x is a vector quantity. That means that delta x can be either positive or negative. So work, though, is a scalar quantity. Work is a positive number if f sub x and delta x are both positive or both negative, in which case the work increases the mechanical energy of the object. If f sub x is positive and delta x is negative, or vice versa, then the work is negative and the object loses mechanical energy. Our equation for work is valid even when the constant force is not parallel to the x-axis. Work is only done by the part of the force acting parallel to the object's direction of motion. We're also showing the units, and so the units of work are joules, and so that's newtons per meter, which equals to kilogram mass squared over second squared. And that will help when, say, you're working through some of the problems associated with this. So let's talk about a constant force F exerted at an angle theta with respect to the displacement delta x. And so the work would then be F cosine theta times delta x. Another definition of work is to relate the work done on an object to the angle the displacement makes with respect to the force. So take a look at the triangle in this figure. The components of the vector F can be written as shown. And so here we have the force. We make a triangle, we use trigonometry. And so with this angle, it's F cosine theta is the amount of force that's going in the x direction, which is the direction of motion. Notice that only the x component, which is parallel to the direction of motion, makes a non-zero contribution to the work done on the object. The work done on an object by a constant force during a linear displacement is shown in the equation, where d is the magnitude of the displacement and theta is the angle between the vector f and delta x. So, so no work is done in a bucket when it is moving horizontally because the applied force is perpendicular to the displacement. So something to think about. We can use our definition for work when the displacement is not specifically along the x-axis or any other axis. In the figure, a man carrying a bucket of water horizontally at constant velocity, the upward force exerted by a man's hand on the bucket is perpendicular to the direction of motion, so it does not work on the bucket. This can be seen from our equation because the angle between the force exerted by the hand and the direction of motion is 90, given cosine 90 degrees is equal to 0. So therefore, the work is W is 0. In the same way, the force of gravity does no work on the bucket. So work always requires a system of more than just one object. A nail, for example, can't do work on itself, but a hammer can do work on a nail by driving it into a board. In general, an object may be moving under the influence of several external forces. In that case, the net work done on the object as it is undergoing some displacement is the sum of the amount of work done by each force. So in this picture, the student does positive work when he lifts the box from the floor because the applied force F is the same direction as the displacement. When he lowers the box to the floor, he does negative work. So work can be either positive or negative. In our definition of work, F and D are magnitudes which are never negative. That means work is positive or negative depending on whether cosine theta is positive or negative. This depends on the direction of the force relative to the direction of the displacement. When these vectors are pointing in the same direction, the angle between them is 0 degrees. So cosine 0 is +1 and the work is positive. For example, when a student lifts a box as shown in the figure, the work he does on the box is positive because the force he exerts on the box is upward. He lifts it in the same direction as the displacement. In lowering the box slowly back down, the student will exert an upward force on the box, but the motion of the box is downward because the vector F and delta X are now in opposite direction. The angle between them is 180 degrees and cosine of 180 degrees is -1. And the work done by the student is negative. So in general, when the part of F parallel to delta X points in the same direction as delta X, the work is positive, otherwise it's negative. So let's think about this a little bit. And so here in the figure below, a block moves to the right in the positive X direction through the displacement delta X, while under the influence of a force with the same magnitude F. Which of the following is the correct order of the amount of work done by the force F, from the most positive to the most negative? And so the answer is C, A, D, and B. And so the reason is that an object that remains at rest has 0 acceleration. However, any number of external forces could be acting on it, providing that the vector sum of these forces is 0. Okay, now we're going to talk about work and dissipative forces. And so the edge of a razor blade looks smooth to the eye if you don't have any magnification, but under a microscope, it proves that it has a number of irregularities. So frictional work is extremely important in everyday life because doing almost any kind of work is impossible without it. Cars couldn't work without friction or conveyor belts or even our muscle tissue. Friction is a complex process and it is caused by numerous microscopic interactions over the entire area of the surface in contact. Imagine a metal block sliding over a metal surface. Microscopic teeth, quote, in the block encounter equally microscopic irregularities in the underlying surface. So if you look at the figure, you might think the edge of the razor blade is smooth, but the figure at the right is a microscopic view showing it has many irregularities. So this figure below, you can see how it is actually irregular. So you can imagine that when the metal block slides over the surface, these irregularities pressing against each other to form, get hot and weld to the opposite surface. Work must be done breaking these temporary bonds, and that comes at the expense of the energy of motion of the block, which we will discuss a little bit later. The energy lost by the blocks goes into heating both the blocks and its environment, with some energy converted to sound. The frictional force of two objects in contact with and in relative motion to each other always dissipate energy in these relatively complex ways. For our purposes, the phrase work done by friction will denote the effect of these processes on mechanical energy alone. So now let's talk about kinetic energy and the work energy theorem. So in the figure, we have an object undergoing a displacement and a change in velocity under the action of a constant net force F sub net. And as you have found, solving problems using Newton's second law can be complicated. An alternative approach is to relate the speed of an object to the net work done on it by external forces. If the net work can be calculated for a given displacement, the change in the object's speed is easy to evaluate. The figure shows an object of mass m moving to the right under the action of a constant net force, also directed to the right. Because the force is constant, we know from Newton's second law that the object moves with constant acceleration. If the object is displaced by delta x, work done by the net force on the object is given by this equation. So you want to recall the relationship for the object undergoing constant acceleration. You can solve this for a delta x and substitute it into the equation for work to get the result as shown. So we're starting to derive these useful equations that we would want to have as we're thinking about the work energy theorem. So to get the net work done on an object equals a change in the quantity of the form 1/2 mv squared. This term carries units of energy, involves the object's speed, so it can be interpreted as energy associated with the object's motion. The kinetic energy of the object of mass m moving with a speed v is defined by the equation shown. Like work, kinetic energy is a scalar quantity. An important result of this is known as a work energy theorem. The net work done on an object is equal to the change in the object's kinetic energy, or the energy change in the kinetic energy is due entirely to the object's change in speed. The proviso on the speed is necessary because work that deforms or causes the object to warm up invalidates this equation, although under most circumstances it remains approximately correct. From our equation, a positive net work means that the final kinetic energy is greater than the initial kinetic energy. This means that the object's final speed is greater than its initial speed. So positive net work increases an object's speed and negative net work decreases its speed. So in this figure, that we have a moving hammer has kinetic energy that can do work on the nail, driving it into the wall. So we can think of kinetic energy as work a moving object can do in coming to rest. For example, suppose a hammer is on the verge of striking a nail, as in the figure. The moving hammer has kinetic energy and so can do work on the nail. The work done on the nail is F delta X, where F is the average net force exerted on the nail, and delta X is the distance the nail is driven into the wall. That work plus small amounts of energy carried away by heat and sound is equal to the change in kinetic energy of a hammer. So we derive the work work energy theorem, assuming that the net force acting on the object was constant. A more general derivation using calculus would show that the result is valid under all circumstances, including the application of a variable force. So we're not dealing with calculus, and what we have is a rigorous enough way of deriving this theorem that it's nice to get that context. So true or false, a block slides at constant speed down a ramp while acting on by three forces: its weight, the normal force, and the kinetic friction. The combined net work done on all three of these forces in the block equals 0. And the answer is true. The net work equals the change in kinetic energy, which in this case equals 0 because the block slides at a constant speed. So true or false, a block slides at constant speed down a ramp while acting on by three forces: its weight, normal force, and kinetic energy. And the question that we want to be thinking about, each force, does 0 work on the block as it slides? Is this true or false? And the answer is false. The gravitational force of weight on the block does positive work as the block slides down the ramp. The normal force does 0 work, and the kinetic force does negative work. And here's another one. So thinking about this, and similar to these other ones, so each force does negative work on the block as it slides. The answer is false. The gravitational force of weight on the block does positive work and the block slides down the ramp. So now let's talk about conservative and non-conservative forces. And so we have a woman diving from a 10-meter platform in this illustration. There are two general kinds of forces. The first is called a conservative force. Gravity is probably the best example of conservative force. To understand the origin of the name, think of a diver climbing to the top of a 10-meter platform. The diver has to do work against gravity in making the climb. Once at the top, she can recover the work as kinetic energy by taking a dive. Her speed just before hitting the water will give her a kinetic energy equal to the work she did against gravity in climbing to the top of the platform, minus the effects of some non-conservative forces such as air drag and internal muscular friction. Here's another one. A man is pulling a sled with a rope at an angle theta from the horizontal. So a non-conservative force is generally dissipative, which means that it tends to randomly disperse the energy of bodies on which it acts. The dispersal of energy often takes a form of heat or sound. Kinetic friction and air drag are a good example. Propulsive forces, like a force exerted on a jet engine or on a plane or on a propeller on a submarine, are also non-conservative work. Work done against a non-conservative force can't be easily recovered. So dragging objects over a rough surface requires work. When the Eskimo shown in the figure drags his sled across terrain, having a non-zero coefficient of friction, the net work is smaller than would be the case of no friction. The missing energy goes into warming the sled and its environment. Losses such as these can't be avoided, and all the energy can't be recovered, so these forces are called non-conservative. So in this figure, we have a couple figures here. So because the first one, because the gravity field is conservative, the diver regains as energy, kinetic energy, the work she did against the gravity is climbing the ladder. Taking the frictionless slide gives it the same result. And then the other figure, because friction is a non-conservative force, a book pushed along the three segments A, B, B, C, and C, D requires 3 times the work as it pushing the book directly from A to D. So we can rewrite the work energy theorem in terms of work done by non-conservative forces and the work done by conservative forces, because the net work is just a sum of these two forces. And so that's what we have here. So you probably have seen this sign driving around, falling rocks, warning sign: an object with kinetic energy, which is energy of motion, can do work on another object. Just like a moving hammer can drive a nail into a wall, a brick on a high shelf can also do work. It can fall off the shelf, accelerate downwards, and hit a nail squarely, driving it into the floorboards. The brick is said to have potential energy associated with it because from its location on the shelf, it can potentially do work. Potential energy is a property of a system rather than of a single object because it is due to the relative positions of interacting objects in the system. So here in the figure, we have a book of mass m falls from a height y sub I to a height y sub f. And so it actually releases some of that energy. So gravity is a conservative force, and for every conservative force, we can find a special expression called a potential energy function. When we evaluate this function at 2 points in an object's path of motion and find the difference, we get the negative of the work done by that force between those 2 points. Potential energy, like work and kinetic energy, is a scalar quantity. So let's take a look at the book and the figure. Let's find the work done by gravity on the book when it moves from one position to another. The negative of that work is the change in the gravitational potential energy of the system. And from that expression, we'll be able to identify the potential energy function. In the figure, the book of mass m falls from a height y sub I to a height y sub f, where the positive y coordinate represents position above the ground. We'll neglect the force of air friction, so the only force acting on the book is gravitation. How much work is done? The magnitude of the force is mg, and that of the displacement is delta y equals y sub I minus y sub f, a positive number with both f and delta y are pointing downwards, so the angle between them is 0. So let's apply our definition of work to this system, where d is y sub I minus y sub f. And factoring out the minus sign was deliberate by the way that the result for gravitational work holds for any object because the gravitational force is conservative. We can include W sub g as a work done by gravity in the work energy equation, where W and C is a work done by the non-conservative forces. Now let's substitute the expression for WG, and next let's isolate W sub NC. And so we can connect the gravitational work and the gravitational potential energy. The gravitational potential energy of a system consists of Earth, and an object of mass m near Earth's surface is given by the equation shown, where g is the acceleration of gravity and y is the vertical position of the mass relative to the surface of Earth or some other reference point. So in this definition, y sub equals 0 is usually taken to correspond to the Earth's surface, but that's not strictly necessary. It turns out that only differences in potential energy really matter. So the gravitational potential energy associated with an object's location near the surface of the Earth is the object's weight, mg, times its vertical position, y, above the Earth. From this definition, we have the relationship between gravitational work and gravitational potential energy. The work done by the gravity is the same as the negative of the change in gravitational potential energy. So this is what we derive there. Okay, so finally, using the relationship shown, we can write an extension of work energy, of the work energy theorem. This equation says that the work done by non-conservative forces, W sub NC, is equal to the change in kinetic energy plus the change in the gravitational potential energy. This equation is true in general, even when other conservative forces besides gravity are present. This work done by these additional conservative forces will again be recast as changes in potential energy and will appear on the right-hand side along with the expression for gravitational potential energy. So let's talk about the reference levels for gravitational potential energy. So in this figure, at any reference level, the desktop, the floor of the room, or the ground outside the building can be used as a reference to represent zero gravitational potential energy in the book Earth system. In solving problems involving gravitational potential energy, it's important to choose a location at which to set the energy equal to zero. This is the same as choosing the place where y equals zero. The choice is completely arbitrary because the important quality, once again, is the difference in potential energy. And this difference will be the same regardless of the choice of zero level. Be aware, though, once you decide on this position, it must remain fixed for the given problem. While it's always possible to choose the surface of Earth as a reference position for zero potential energy, the problem statement of a problem will usually suggest a convenient point to use. So for example, consider a book at several positions located in the figure. When the book is at A, a natural zero level for potential energy is the surface of the desk. When the book is at B, the floor might be a better convenient reference level. And finally, the location of C, where the book is held out at a window, the surface of Earth is a logical choice for the zero level of potential energy. The choice, however, makes no difference. Any of these three reference levels could be used as a zero level, regardless of whether the book is at A, B, or C. So in terms of gravity and the conservation of mechanical energy, conservation principles play an important role in physics. When a physical quantity is conserved, the numeric value of the quantity remains the same throughout the physical process. Even though the form of the equation may change in some way, its final value is the same as its initial value. The kinetic energy of an object falling only under the influence of gravity is constantly changing, as is the gravitational potential energy. Obviously, then, these quantities aren't conserved because we assume that all non-conservative forces are absent. We can set W sub n C equals to 0 in our equation. Let's rearrange these equations. We get a very interesting result. According to this equation, the sum of the kinetic energy and the gravitational potential energy remains constant at all times, and hence is a conserved quantity. We denote the total mechanical energy by E, which is equal to KE plus PE, and say that the total mechanical energy is conserved. So here in this picture, a student throws 3 identical balls from the top of a building, each at the same initial angle, but at different, each at the same initial speed, but at a different initial angle. So imagine tossing a rock off the side of a building. Let's ignore any drag forces. As the rock falls, its speed increases, so its kinetic energy increases. As the rock approaches the ground, the potential energy of the rock Earth system decreases. Whatever potential energy is lost as the rock moves downward appears as kinetic energy, and our equation says that in the absence of non-conservative forces like air drag, the trading of energy is exactly even. This is true for all conservative forces, not just gravity. In any isolated system of objects interacting only through conservative forces, the total mechanical energy of the system remains the same at all times. If the force of gravity is the only force doing work within a system, then the principle of conservation of mechanical energy takes the form shown. Thus, the form of the equation is particularly useful for solving problems explicitly involving only one mass, only in gravity. In that special case, which you will see fairly often, notice that the mass cancels out of the equation. So want to keep in mind that though that is possible only because any change in kinetic energy of the Earth is in response to gravity, to a gravity field of the Earth of an object mass M has been neglected, and rightfully so. In general, there must be kinetic energy terms for each object in the system and gravitational potential energy terms for every pair of objects. Other terms have to be added when other conservative forces are present, as we'll introduce in the near future here. So let's have a question to review some of this. And so we have three identical balls are thrown from the top of a building, all with the same initial speed. The first ball is thrown horizontally, the second at some angle above the horizon, and the third at some angle below the horizon, as shown in the figure. Neglecting air resistance, rank the speed of the balls as they reach the ground from fastest to slowest. And so the answer is all three balls strike the ground at the same speed. So all three balls have the same speed the moment they hit the ground, because all start with the same kinetic energy and undergo the same total change in gravitational potential energy. Here's another question. So Bob of mass M drops from a tree limb at the same time that Esther, who has a mass M, begins her descent down a frictionless slide. If they both start at the same height above the ground, which of the following is true about the kinetic energy as they reach the ground? So the answer is they have the same kinetic energy. So the reason is they start from rest. So the initial kinetic energy is 0 for each of them. They have the same mass and start from the same height. So they have the same initial potential energy. Since neither spends energy overcoming friction, all of their original potential energy will be converted into kinetic energy as they move downwards. Thus, they will have equal kinetic energies when they reach the ground. So once again, these are useful charts when we start thinking about how we would answer, how we would go about solving these kind of questions. So here is a problem-solving strategy, applying conservation of mechanical energy. So the first thing you want to do is you want to define the system, including all interacting bodies. Verify the absence of non-conservative forces. That a valid assumption that you can use. Number two, you want to choose a location for y equals 0, the zero potential for gravitational potential energy. Number three, you want to select the body of interest and identify 2 points, one point where you have a given information and the other point where you want to find out something about the body of interest. Write down the conservation of energy equation from the system, identify the unknown quantity of interest, and then 5, solve the unknown quantities, which is usually either a speed or a position, and substitute known values. It's usually best to do the algebra with symbols rather than substituting known numbers first, because it's easier to check the symbols for possible errors. The exception is when the quantity is clearly 0, in which case you can immediately substitute 0, which will greatly simplify your algebra. So let's talk about spring potential energy. So in the figure, we have a spring at equilibrium, neither compresses nor stretching. In B, we have a block of mass M on a frictionless surface is pushed against the spring. And C, when the block is released, the energy stored in the spring is transferred to the block in the form of kinetic energy. So let's take a look at springs. Springs are found in machines of all kinds, in watches, toys, cars, and trains, as well as other biological systems that we could talk about that store mechanical energy, including some types of fish. They have the ability to store mechanical energy like this with their jaw, based on different kinds of setups that they have there. Work done by an applied force in stretching or compressing a spring can be recovered by removing the applied force. So like gravity, the spring force is conservative as long as losses through the internal friction of the spring can be neglected. This means a potential energy function can be found and used in the work energy theorem. So the top figure shows a spring in its equilibrium position where the spring is neither compressed nor stretched. The bottom figure shows someone pushing a block against the spring, hence compressing it at distance x. Here, x represents a displacement from the equilibrium position, which for our purposes will always be taken to be at x equals 0. Experimentally, it turns out that doubling a given displacement requires twice the force, and tripling will take 3 times. This means that the force exerted by the spring must be proportional to this displacement. shown in the equation where K is a constant of the proportionality, the spring constant carrying units of newtons per meter. So this equation is called Hooke's law after Sir Robert Hooke, who discovered the relationship. The force F sub s is often called a restoring force because a spring always exerts a force in the direction opposite the displacement of its end, tending to restore whatever is attached to the spring to the original position. For positive values of x, the force is negative, pointing back towards equilibrium at x equals 0. And for negative x, the force is positive, again pointing towards x equals 0. For a flexible spring, K is a small number, maybe about 100 newtons per meter, but for a stiff spring, K is large, say 10,000 newtons per meter. The value of the spring constant K is determined by how the spring was formed, its material composition, the thickness of the wire. The minus sign ensures that the spring force is always directed back towards the equilibrium point. So in this figure, we have a spring at equilibrium, neither compressed nor stretched, and the elastic potential energy is associated with the spring force. The elastic potential energy is another way of looking at the work done by a string during motion because it is equal to the negative of the work done by the spring. It can be considered stored energy from the work done to compress or stretch the spring. So take a look at the spring in the figure. Let's find the work done by the spring when compressed by an applied force from equilibrium to a displacement x. The spring force points in the direction opposite the motion, so we expect that the work to be negative. In this case, because this is a varying force, we can use the average force to find the work done by the spring force, and the work done by the spring force is given by the equation shown. So in general, when the spring is stretched or compressed from xi to x sub f, the work done by the spring is given by the equation for W sub s. The work done by the spring can be included in the work energy theorem as shown, where P E sub G is the gravitational potential energy. The elastic potential energy associated with the spring force is P E sub s, where K is a spring constant and X is the distance to the spring is stretched or compressed from equilibrium. The quantity P E sub s is often called the spring potential energy. To differentiate it from the form of elastic potential energy, such as that of rubber bands or piano strings, which have a different mathematical formula. We can use this expression to write a new form of the work energy theorem, including both gravitational electrical potential energy, where W sub nc is a work done by the non-conservative forces, Ke is the kinetic energy, and Pe sub g is a gravitational potential energy. And Pe sub s is the elastic potential energy. Pe, which we used before to denote the gravitational potential energy alone, will from now on denote the total potential energy of a system, including potential energies due to all conservative forces acting on the system. So we're getting a little bit more complicated as we introduce different types of forces. So in this figure, when the block is released, the energy stored in the spring is transferred to the block in the form of kinetic energy. So the figure shows how the stored elastic potential energy can be recovered. When the block is released, the spring snaps back to its original length, and the stored elastic potential energy is converted to kinetic energy of the block. The elastic potential energy stored in the spring is 0 when the spring is in the equilibrium position. That is K equals 0. Potential energy is stored in the spring when it is stretched. The elastic potential energy is a maximum when the spring has reached its maximum compression or extension. Finally, the potential energy is always positive when the spring is not in the equilibrium position. In the absence of non-conservative forces, so we can write an extended form for the conservation of mechanical energy as we're showing here. So let's do a few questions here as we're going through this topic. Calculate the elastic potential energy of a spring with a spring constant K equals 225 newtons per meter that is compressed by 1 times 10 to the 22 meters. So the answer is 1.13 times 10 to the minus 2 joules. And so the reason is the elastic potential energy is PE sub S equals to 1/2 K x squared, where x is the displacement from the equilibrium where the spring is compressed. And so we have the compression x compressed is equal to -1 times 10 to the minus 2. And therefore, we can do our calculations for x squared and PE sub S and do the math and come up with the answer. So here is another one. So calculate the electric potential of a spring with an energy constant of 225 newtons per meter, and that is stretched by a positive 1 times 10 to the 22 meters. So we have either stretched, the last one was compressed, and the other one here is stretched. And so, as you can imagine, that what this ends up being, but the potential energy is still the same amount. Okay, true or false? The elastic potential energy of a stretched or compressed spring is always positive. And so once again, we're talking about potential energy. And so, yes, it is true. Elastic potential energy depends on the spring constant and the distance that the spring is stretched or compressed. By what factor does the elastic potential energy change if the spring is stretched is doubled? And so the answer is 4. The elastic potential energy scales with x squared. So as the stretch is double, the potential increase is 2 to the second, which is 4. 2 times 2, which is 4. So the elastic potential energy depends on the spring's constant and the distance the spring is stretched or compressed. By what factor does the elastic potential change if the spring stretch is tripled? And so this is similar to the last one. It's 3 squared, which is 9. So let's talk about systems and energy conservation. You may remember that the work energy theorem can be written as shown. As we have seen, any work done by conservative forces such as gravity and springs can be accounted for by changes in potential energy. The work energy theorem can be written as shown, where now PE includes all potential energies. So let's rearrange this equation. The total mechanical energy is given by E equals KE plus PE. And so let's make substitution into our equation. The results are that the work done on a system by all non-conservative forces is equal to the change in the mechanical energy of that system. If the mechanical energy is changing, it has to be going somewhere. So the energy either leaves the system and goes into the surrounding environment, or stays in the system and isn't converted into a non-mechanical form such as thermal energy. An example is thinking of a block sliding along a rough surface. Friction creates thermal energy, absorbing partly by the block and partly by the surrounding environment. When the block warms up, something called internal energy increases. The internal energy of a system is related to the temperature, which in turn is a consequence of the activity of its parts, such as the motion of atoms in a gas or the vibration of atoms in a solid. So energy can be transferred between a non-isolated system and its environment. If positive work is done on the system, energy is transferred from the environment to the system. If negative work is done on the system, energy is transferred from the system to the environment. So far we have been encountering three methods of storing energy in a system: kinetic energy, potential energy, and internal energy. However, we've seen only one way of transferring energy into or out of a system: through work. Other methods will be studied in later topics, but let's go ahead and summarize them here. Work, in the mechanical sense of the topic, transfers energy to a system by displacing it with an applied force. Heat is a process of transferring energy through microscopic collisions between atoms or molecules. For example, a metal spoon resting on a cup of coffee becomes hot because some of the kinetic energy of the molecules in the liquid coffee is transferred to the spoon as internal energy. Mechanical waves transfer energy by creating disturbances through propagation through air or another medium. For example, energy in the form of sound leaves your stereo system through the loudspeakers and enters your ears to simulate hearing process. Other examples of mechanical waves are seismic waves and ocean waves. Electrical transmissions transfer energy through electrical currents. This is how energy enters your stereo system or any other electrical device. And then finally, electromagnetic radiation transfers energy in the form of electromagnetic waves, such as light, microwaves, and radio waves. Examples of this method of transfer includes cooking a potato in a microwave oven and light energy traveling from the sun to the earth through space. So a couple things for you to be thinking about. I threw this in. So in our textbook, one of the things they have is a whole bunch of places where there's applications and biological applications. And since a lot of you are falling into that area, I wanted to be pointing this out. And periodically in our discussion, and we can be bringing these things up, and also with the project work that I'm hoping that you guys will have fun with, you can also be thinking about this. And so here we can be thinking about conservation of energy in general. The most important feature of the energy approach is the idea that energy is conserved. If it can't be created or stored, only transferred one form to another. The principle of conservation of energy is confined to physics. In biology, energy transformation takes place in a myriad of ways of living systems. So one example is a transform of chemical energy to mechanical energy that causes flagella to move and propel an organism. Some bacteria use chemical energy to produce light. And so this is just a picture of flagella that illustrate bioluminescence. So this is a process in which chemical energy is converted to light. And so that's another type of energy transfer that still falls under conservation of energy. So we've seen this figure before. So you can, the context for this, and unfortunately I need to update this with another picture, but this small plant found in southern waters exhibit bioluminescence, a process in which chemical energy is converted to light. The red area of those. Hold on just a second. Okay, this is just, I just already read that to you, so I'll just skip that. So now we're going to be talking about conservation of energy in general. And so let's just introduce this through a way for us to engage on these topics a little bit here. And so a book of mass m is projected with a speed v across a horizontal surface. The book slides until it stops due to friction forces between the book and the surface. The surface is now tilted 30 degrees, and the book is projected up the surface with the same initial speed v. When the book has come to rest, how does the decrease in mechanical energy of the book earth system compare to when the book was slid over the horizontal? And so the answer is it's smaller on the tilted surface. The decrease in mechanical energy of the system, F sub x times delta x, there has a smaller value on the tilted surface for two reasons. The force on the kinetic friction is smaller because the normal force is smaller, and the displacement delta x is smaller because a component of the gravitational force is pulling the book in the direction opposite to the velocity. Okay, let's talk about power now. Power is a rate at which energy is transferred. It is important in the design and the use of practical devices such as electrical appliances and the engines of all kinds, and in the understanding of living creatures, because the maximum work per second or power output of an animal varies greatly with output duration. Power is defined as a rate of energy transferred with time. If an external force does work, W on an object in the time interval delta t, then the average power delivered to the object in the work done divided by the time interval. Let's rewrite our equation for average power by making a substitution. Notice that delta x over delta t is the average velocity of the object during the time delta t. According to this result, average power is a constant force times the average velocity. The force F is the component of force in the direction of the average velocity. A more general definition called the instantaneous power can be shown with a little calculus and has the same form in this equation. Both the force F and the velocity V must be parallel, but can change with time. So let's continue on with this. The SI units of power is the joule per second, also called the watt, made by James Watt. The unit of power in the US customary system is horsepower. The horsepower was first defined by Watt, who needed a large power unit to rate the power output of his new invention, the steam engine. The watt is commonly used in electrical appliances, but it can be used in other scientific areas as well. For example, the European sports cars are rated in kilowatts. In electrical power generation, it is customary to use the kilowatt hour as a measure of energy. 1 kilowatt hour is the energy transferred in 1 hour at the constant rate of 1 kilowatt, which is 1,000 joules per second. It is important to realize that a kilowatt hour is a unit of energy, not power. And when you pay your electrical bill, you're buying energy, and that's why your energy bill lists a charge for electricity of about 10 cents per kilowatt hour. The amount of electricity used by an appliance can be calculated by multiplying its power rating, usually expressed in watts, and valid only for normal household electrical circuits, by the length of time that the appliance is operated. So let's talk about energy and power in a vertical jump. So in the figure, we see the extension and free flight in vertical jump, seeing some characteristics of that. So we want to be thinking about jumping straight up as shown in the figure. The stationary jump consists of two parts, extension and free flight. In the extension phase, a person jumps up from a crouch, straightens the legs, and throws up the arms. The free flight phase occurs when the jumper leaves the ground, because the body is an extended object and different parts move with different speeds. We describe the motion of the jumper in terms of the position and velocity of the center of mass, which is the point in the body at which all mass may be considered to be concentrated. The figure shows the position and velocity of the center of mass at different stages of the jump. Using the principle of conservation of mechanical energy and taking P, E, so I, the gravitational potential energy of the jumper Earth system, just as the jumper lifts off from the ground, to be zero, and noting that the kinetic energy Ke sub F of the jumper at the peak is zero, we can find H, the maximum increase in height of the center of mass. We can also estimate V sub Cm by assuming that the acceleration of the center of mass is constant during the extension phase. If the depth of the crouch is h and the time for extension is delta t, we find the results shown. So measurements on the ground of a male college student shows typical values of H equals 0.4 meters, delta T equals 0.25 seconds, and the time set by the fixed speed with which the muscles can contract. So we can plug our values and see what we get to show the equations. Now we can calculate the kinetic energy for this jumper, assuming a mass of 68 kilograms to show the equation. It might seem like this is a large expenditure of energy, but let's make a simple calculation to show that jumping and exercise in general are not good ways to lose weight in spite of their many health benefits, because the muscles are at most 25% efficient at producing kinetic energy from chemical energy. Muscles always produce a lot of internal energy and a kinetic energy as well as work. That's why you perspire when you work out. They use it 4 times, that is 350 joules, which is about 1,400 joules of chemical energy in one jump. This chemical energy ultimately comes from food we eat, with energy content given in units of food calories, and 1 food calorie is equal to 1,400 joules. So the total energy supplied by the body as internal energy and kinetic energy in a vertical jump is about 1/3 of 1 food calorie. So not a whole lot. Finally, it's interesting to calculate the average mechanical power that can be generated by the body in strenuous activities for brief periods. Here you find that humans can produce about 2 horsepower of mechanical power for periods on the order of seconds. The table shows the maximum power output for humans for various periods while bicycling and rowing, which are activities in which it is possible to measure power outputs accurately. And so here we just see a range of what that would look like. What about power done by a varying force? The work done on a particle by the force component F sub x for the small displacement delta x is approximately Fx times delta x, the area of the shaded rectangle. And the width delta x of each rectangle is shrunk to 0. Imagine an object is displaced along the x-axis under the action of force that acts in the x direction and varies with position. The object is displaced in the direction of increasing x from x sub I to x sub f. In such a situation, we can't use W equals Fd to calculate the work done by the force, because this relationship applies only when F is constant in magnitude and direction. But let's imagine the object undergoes the small displacement delta x shown in the graph on the left. Then the x component of the force is nearly constant over this interval, and we can approximate the work done by the force for this small displacement as shown. The quantity is just the area of the shaded rectangle in the figure. If we imagine that the curve of F versus X is divided into a large number of such intervals, then the total work done for the displacement from X sub I to X sub F is approximately equal to the sum of the area of the large number of small rectangles. Now let's imagine going through the same process where twice as many intervals, each half the size of the original delta X. The rectangles then have smaller widths. They are better approximate the area under the curve. Continuing this process of increasing the number of intervals while allowing the size to approach 0, the number of terms in the sum increases without limit, but the value of the sum approaches a definite value equal to the area under the curve bound by F sub x and the x-axis in the figure on the right. In other words, the work done by a variable force acting on an object that undergoes a displacement is equal to the area under the curve of the graph Fx versus x. And so that's what we're seeing here. And once again, alluding a little bit to some calculus. So in the figure, we have a block being pulled from xi equals 0 to x sub f's equals X max on a frictionless surface by a force F app. And then B, a graph of F app versus X. So we're seeing how that looks. So the block on a horizontal frictionless surface connected to a spring shown in the figure is a common physical system where forces vary with position. When the spring is stretched or compressed a small distance X from its equilibrium, position X equals 0, it exerts a force on the block given by the equation F sub X equals minus Kx, where K is a force constant of the spring. Now let's determine the work done by an external agent on the block as the spring is stretched very slowly from X sub I equals 0 to F sub X equals X max. This work can be easily calculated by noting that any value of the displacement, Newton's third law tells us that the applied force is equal in magnitude to the spring force and acts in the opposite direction. So plot of F sub app versus X is a straight line as shown in the figure on the right. That means that the work done by the applied force is stretching the spring from X equals 0 to X equals X max in the area under the straight line in this figure, which is the case in this area of the shaded triangle. During the same time that the spring has done exactly the same amount of work, but that work is negative because the spring force points in the direction opposite the motion. The potential energy of the system exactly equal to the work done by the applied force and is the same sign, which is why potential energy is thought as stored work. So we have a bunch of questions here just that are summing up what we have talked about. I'm just going to quickly give you the answers and you can look these over with more time and pause the recording. So in which of the following case would you do the least amount of work? And the answer is 1. So keep that in mind. This next one is 2 blocks with mass M2 greater than M1 are pulled as shown along the horizontal surface, each at constant speed. Which tension force does more work moving the block at distance d along the surface? And the possible answers are 2 and 7. So you could just justify those by thinking about that. And so what this is trying to give you some insight as to how to integrate force ideas and work ideas. This one is now both are pulled at a constant speed, but V2 is greater than V1. Which tension force does more work moving the block at distance d along the surface? And the answer is T2. The answer for this one is T1. The answer for this, both have the same speed. This one, again, they both have the same speed. The answer for this one is none of the above. The answer for this one is 4. I'll just skip over this one. The answer for this, the ball on track B. The answer for this one, the ball on track B wins by a large margin. And finally, just to have a few summary charts, we've covered a lot of material here. So we've talked about work. Work done on an object by a constant force is given by the equation shown, where F is the magnitude of the force, D is the magnitude of the object's displacement, and theta is the angle between the direction of the force F and the displacement delta X. As you can see in the figure, solving simple problems requires substituting values into this equation. More complex problems, such as those involving friction, often require using Newton's second law to determine forces. Then we have a kinetic energy in the work force theorem. The kinetic energy of a body with mass m and speed v is given by the equation shown. The work energy theorem states that the net work done on an object of a mass m is equal to the change in the kinetic energy. Work and energy of any kind carry units of joules. Solving problems involve finding the work done by each force acting on the object and summing them up. which is W sub net, followed by substituting quantities into the work energy theorem and solving for the unknown quantity. Conservative forces are special. Work done against them can be recovered. It's conserved. An example is gravity. The work done in lifting an object through a height is effectively stored in the gravity field and can be recovered in the kinetic energy of the object simply by letting it fall. Non-conservative forces such as surface friction and drag dissipate energy in a form that can't be readily recovered. To account for such forces, the work energy theorem can be written as shown, where W sub MC is the work done by non-conservative forces and WC is the work done by conservative forces. Gravitational potential energy, gravity and non-conservative forces. The gravitational forces in a conservative field, gravitational potential energy is another way of accounting for gravitational work W sub G. To find the change in gravitational potential energy as an object of mass m moves between 2 points in a gravitational field, we substitute the value of the object's y coordinates. The work energy theorem can be generalized to include gravitational potential energy. Gravitational work and gravitational potential energy should not both appear in the work energy theorem at the same time, only one to the other because they're equivalent. Setting the work due to non-conservative forces to 0 and substituting the expression for KE and PE, a formula of conservation of mechanical energy with gravitation can be obtained as shown. To solve problems with this equation, identify 2 points in the system, one where information is known and the other where the information is desired. Substitute and solve for the unknown quantities. We talked about spring potential energy. The spring force is conservative. Its potential energy is given by the equation shown. And spring potential energy can be put into the work energy theorem where non-conservative forces are absent and W sub NC equals to 0 and the mechanical energy is conserved. And finally, for systems energy conservation, the principle of conservation of energy states that energy can be created or destroyed. It can be transformed, but the total energy content of any isolated system is always constant. The same is true for the universe at large. The work done by all non-conservative forces acting on a system equals the change in the total mechanical energy of the system, where PE represents all potential energies present. All right, well, thank you very much. We covered a lot of ground there. So we'll just finish the lecture and call it an end for this content. Thank you.